Hi folks, welcome back. I hope you're all doing well. So today I want to take a look at a paper from back in 2009 that calls out a very important but also often overlooked aspect in CS systems papers, and that is measurement bias. So what is measurement bias? Measurement bias happens when a seemingly unrelated change in your experimental setup swings the data to such an extent that it causes you to draw incorrect conclusions. What the authors found was that within computer science systems research, measurement bias was both significant as well as commonplace. And what they mean by that is that it is significant in the sense that measurement bias can overstate an effect or sometimes simply lead to an incorrect conclusion about the effect even being present. And it is commonplace because the authors found this to occur in most major architectures, most major compilers, and most commonly used benchmarks. Now, the coolest part of this paper is that they make their arguments really concrete by actually demonstrating a real example of measurement bias. So they set up an experiment in this paper. The question they're asking is whether O3 or O2 optimizations in a C compiler are faster. So when you compile with most C compilers, they have various optimization flags that you can pass through the command line. One of them is -O2, another one is -O3, with -O3 generally thought of as being the set of more aggressive optimizations. So the question is pretty simple, right? You have a bunch of source code or a bunch of benchmarks. You compile the whole thing with -O2. You run it and see how long it takes. Then you compile all of the code with -O3 and do the same thing and see which one is faster. It seems like a very simple toy experiment. And yet, extremely surprisingly, what the authors show over here is that two seemingly trivial and unrelated parts of the experimental setup completely swing the data in either direction. And those are the Unix environment size, which is to say how many environment variables you have and what is the size of the values of those environment variables. And number two, the link order, which is simply the textual order in which the object files are provided to the linker to build the final executable. The first experiment looks at linking order. And what they do is they look at the default linking order, they look at alphabetical linking order, and then they try a number of randomly generated linking orders. What you see on the y-axis is the number of cycles that the final executable runs for, and the ratio between O2 and O3. So the number of cycles the O2 compiled program takes divided by the number of cycles that the O3 compiled program takes. And as you can see, this is all over the place. Sometimes O2 is faster, sometimes O3 is faster. And notably, you'll see that in one of the random linking orders, O3 is the fastest among all orders. And in another random linking order, O2 is the fastest among all linking orders. The second effect, which is the effect of the Unix environment size, is even more surprising. All they're doing is increasing the string value of a dummy environment variable by 63 bytes at a time. And here again, they find that the environment size has a significant effect on the outcome of this benchmark. In particular, you'll see that just around the 2000 bytes mark, there's one setup in which O2 is much faster than all the other readings, and another one where O3 is much faster than all the other readings. So what is causing these swings? What is causing this measurement bias? If you look at the first case where we changed the order in which object files were linked, that mostly seems to be about how the layout of the code interacts with the instruction cache of the hardware. because the link order changes the alignment of the code within the executable and where that code gets loaded within the entire executable. But as the authors point out later in the paper, one of the problems with accurately verifying this hypothesis is that the processor doesn't give you enough low-level performance debugging information to say for certain that this is the case. And what about the case where we change the Unix environment size? It has a similar reason, but for data rather than code. So changing the environment size affects where the stack starts. And that effectively means that changing the environment size changes the alignment of the stack, and that once again affects how the stack ends up getting cached within the processor. The authors actually went one step further to rule out GCC alone as the cause of this measurement bias. They went ahead and repeated the entire experiment with Intel's C compiler and got the same measurement bias. And the authors are trying to highlight how big of a problem this really is for systems research, because in a bunch of recent prominent CS systems conferences, they found that none of the papers addressed this issue properly. How can we avoid this? What is the solution to measurement bias? The authors look to other scientific fields that have had to live with this problem for a long time and have come up with solutions to deal with it. They make the analogy with the small town polling problem, which is that if you want to predict the outcome of a nationwide election, you wouldn't try to do that by polling just one small town. You would try to poll a large cross-section of the population, which in CS research means that you want to have a diverse set of benchmarks or a large set of experimental setups, or both. One way to do that might be to vary some of the parameters in your experiment setup on a random basis. The other way is to have more rigorous causal analysis to make sure that the effect you're seeing is indeed caused by the changes that you made. As the authors point out over here, the second step, causal analysis, is not trying to clean up the data. It's not trying to get untainted data. Instead, it's trying to establish confidence in the conclusion, even in the presence of biased data. So that was a really interesting paper that called out how commonplace and how significant and yet how overlooked measurement bias is in computer science systems research, and suggests some techniques for overcoming it. I hope you enjoyed that, and I will see you next time. Thank you very much.